So we have been talking about time response specifications of second order systems. So we took uh, two types of responses on the last turn. We talked about on the last turn we talked about overdamped response, and we talked about undamped response, right? So overdamped response we saw for a step input when it is given to a system which has pole locations like this. On the left half plane, negative poles, negative real parts, and we saw that undamped response is for a second order system which has complex poles on the j omega axis. So now today we are going to see two more types of responses. The third important type of response is the underdamped response. So it is in between these two responses. So here you don't have any damping. In this you have a lot of damping. So the system here is slow, and the system here is so fast that it is continuously oscillating. So the third option that you have is in between the two responses. So for the underdamped response, let us take an example. Let us suppose that our transfer function gs is given by say 1 upon s square plus 2s plus 2, and let us suppose this plant we are applying a step input as we have been doing before, and we want to see the output in as a function of time, right? So we can write down the equation for cs. It is 1 upon s into s square plus 2s plus 2, because your step input is 1 by s. So you have to now apply partial fraction expansion on this in order to find out ct. So we can break this up. Now you can see that I have taken a system which has complex poles. So s square plus 2s plus 2 has complex poles. So you cannot break it down like we broke down on the last turn. We had s square plus 5s plus 6, and we broke this down into s plus 3 into s plus 2. So we broke this down into real poles. Now this is not possible in this case because the determinant is negative, right? So in such a case, the factorization that you have to do is to be of the form s plus alpha whole square plus beta square, right? This is what we have to do in this case. So what we'll do is we'll first write this down as a by s plus b by s square plus 2s plus 2, and then we'll figure out what to do with this s square plus 2s plus 2. Now I've told you this in the previous class that we can write this as a by s, and we can write this as a whole square, which is s plus 1 whole square plus some other term, whatever is remaining, right? So when we write it in this form, we'll get expression of the form s plus alpha whole square plus beta square in the denominator, and we already know that the Laplace inverse of s plus alpha whole square plus beta square, if you want to do the Laplace inverse of a term like this, you get e to the power minus alpha t cos beta t. And if instead of s plus alpha in the numerator, if you have beta in the numerator, then you will get the Laplace inverse as e to the power minus alpha t sine beta t. So this is already known, so that is why we write it like this. Now you can compare this to your original equation, which is 1 by where you have 1 by s into s square plus 2s plus 2, and try to find out the values of a and b. This is very simple. You'll find that A is equal to 1 and B is equal to minus S plus 2, right? This is actually BS plus C, I'm sorry. So B would be minus 1 and C would be minus 2, right? So basically you open up your CS and you write it like 1 by S minus S plus 2 divided by S plus 1 whole square plus 1, right? So you can multiply the two sides and you'll see that this is S square plus 2S plus 2 minus S square minus 2S, and you're left with 2 at the end, right? So this is S square plus 2S plus 2 minus S square minus 2S. So you're left with 2. So you have to put a half here, right? 1 by 2 of this, right? So actually your A would be 1 by 2, your B would be minus 1 by 2, and your C would be minus 2 by 2. So now you can open this up and you can write down, if you take your inverse Laplace transform, you can write down Ct as half 1 minus, you can write this as 1 by S minus, here you'll write S plus 1 divided by S plus 1 whole square plus 1, and then you can write this as S plus 1 whole square plus 1. So this is your CS, sorry. So you can take the inverse Laplace transform and write your Ct as half. The inverse Laplace of 1 by S would be 1. The inverse Laplace of S plus 1 divided by S plus 1 whole square plus 1 is going to be e to the power minus t cos t. Omega is 1, A is 1. And then this would be e to the power minus t sine of t. Now this is your Ct. If you want to sketch this, you can use MATLAB to sketch it. It's very simple to sketch something like this. You will see that the response Ct as a function of time is going to be something like this. So it is somewhere between being very slow and between an oscillatory response. So the response is moving from 0 to 1. It's overshooting, and then it is oscillating about the mean position till it finally comes down to settles down at the steady state value. So this is one response, and this is obtained if you look at the poles of this function and this transfer function that we took, which was S square plus 2S plus 2. You will see that the poles are at minus 1 minus j and minus 1 plus j. So you have this pole at minus 1 plus j and this pole at minus 1 minus j. Sorry, they will be on the left half of the S plane, right? So it's like this, minus 1 minus j and minus 1 plus j. The last type of response is called the critically damped system. Critically damped response, and your critically damped response is actually present when your poles are real and they are equal. So this is for real and equal poles, right? So if you have real and equal poles, what is going to happen? Now let us take a system like that. So a system, again I'll take an example, is 1 by S plus 1 whole square, for example. So my step input is 1 by S. This means that my output is 1 by S into S plus 1 whole square, and I have to basically go for Laplace. I have to go for partial fraction expansion. So I write A by S plus BS plus C divided by S plus 1 whole square. I open this up and compare it to the CS. I'll get 1 by S minus S plus 2 divided by S plus 1 whole square. Do I get this? So this is s square plus 2s plus 1 minus s minus s into s square plus minus 2s, right? So s square and s square cancel, so I'll left with this. Yes, so I'll get this values of a, b and c corresponding to this. A is 1, b is 1 and c is 2. So you can open this up further in order to solve it. So this will be s plus 1 divided by s plus 1 whole square minus 1 divided by s plus 1 whole square, and this is going to be 1 by s minus 1 by s plus 1 minus 1 by s plus 1 whole square. And if you take the Laplace inverse of this to find c of t, you'll get 1 minus e to the power minus t minus t e to the power minus t. And this kind of a response is for poles which are like this, which are real and equal, and of course negative. And if you sketch this response, it's going to be critically damped. That means that the damping is just perfect in the sense that it is neither too fast nor too slow. So this is your response going to be. And if you on the same plot, if you sketch the overdamped response, it would look like this. And this on the same plot, if you sketch the underdamped response, the one that we just did, would be something like this. And on the same, if you sketch the critically damped response, I'm approximately sketching it, right? So that should be something like this, right? Maybe the overshoot is more. This is just to give you an idea about the 4 types of responses. So this type of a response is the one that is in red, is called the critically damped response. So we have seen that for second order systems, the response is more complicated, and we have just taken step input. And we have taken second order systems. Some examples of second order systems. We have seen 4 types of pole locations, but all of them on the left half plane or on the j omega axis. So what is going to be the case if the pole of the second order system is not on the left half plane but on the right, but in the right half plane? So what is going to happen if you have poles like this, right? So we'll see this also, because we don't analyze these responses as much, because actually these would be unstable systems. The responses would be unstable, but we still can have an idea about what the response is going to be. See, if you had poles here, you basically wrote your equation as s plus alpha whole square plus beta square, right? Where alpha and beta were positive quantities, right? Greater than 0. Only then, because when you wrote it like this, you were able to write s is equal to s plus alpha whole square is equal to minus beta square. That means s plus alpha whole is equal to plus minus j beta. That means s is equal to minus alpha plus minus j beta. And here you have s is equal to minus alpha, and this is your beta. So this is plus j beta, and this is minus j beta. So this is plus j beta and minus j beta. So basically you have complex poles with negative real parts. Now if you have complex poles with positive real parts, that means they would, here in this case, this minus alpha would be replaced by plus alpha. And if that happens, that means this term here is going to be negative. Now if this term here is going to be negative, your poles would be at alpha plus minus j beta, which is here, alpha plus minus j beta. Now what is going to happen? See, the Laplace inverse of 1 upon s plus alpha whole square plus beta square terms of this form, the Laplace inverse is e to the power minus alpha t, either cos omega t or sin cos beta t or sin beta t. So I'll write cos beta t plus phi. So the responses are of this form. Now if instead of this plus sign here you have a minus sign, that means the poles are on the right half plane. You have, instead of this plus sign here, minus sign here, you have a plus sign. So the response is of the form e to the power alpha t cos beta t plus 5. So this is an exponentially increasing response, although it is oscillating. So your underdamped response was like this, where the oscillations were damping out, but this is an overdamped response. This is an unstable response, and this response is going to be something like, your oscillations are continuously increasing, right? So that is why we don't study these responses in detail, because whenever we have a pole which has a positive real component, that is anything on the right half plane, right? Anything on the right half plane, that will lead to a response that is going to increase without bound. So it is increasing, right? And it is increasing without bound. So at infinity, the response is going to be infinity. So this kind of a response is called an unstable response. We'll study stability in more detail, but basically I told you this so that you understand that all our poles are on the left half plane, because any pole on the right half plane, any pole on the right half plane means that the response is unstable, and we are not interested in studying it. We are interested in analyzing stability, but we are inherently interested in using stable systems for our design, right? So with this I end this lecture with the basic understanding that we have understood what the four main types of stable second order responses to step inputs are. Thank you very much.